Hello everyone. Discuss contest 14 today. Contest was much easier than the previous one. I hope you liked it much more because that's much closer to normal difficulty that I usually want for these contests. Um, okay. So some people solve. Okay, I'm not sure what's problem C. Okay, we'll discuss problem C. What you can probably go wrong in problem C. Uh, Last few problems are kind of interesting. First problems are simple, but still kind of interesting. So we'll discuss all of them. So the first problem is uh, purely technical. So no special algorithms needed, no idea needed. Just need to implement what's described in the problem statement. I tried to do it a little bit more programmistic, let's say. So instead of having multiple ifs, I just tried to put everything in array because that's normally what you think to normally. It took a lot of time actually to transform this. Probably would be better to have some, I don't know, some regular expressions to transform it. But yeah, so that's what I do here. So I make all, just transform this uh, list to something I can use in my program. Yeah. So yep. So this, I have list of pairs. Just transform here. That's it. After that, the rest is kind of easy. So you read the data and remove the stones corresponding to these colors. So I just put all the stones to this set, and then remove the stones which I have in this in the input. Uh, Again, it would make much more sense to have map from string to string actually, but at this point I decided I will not change this. I will just, because I have small numbers, I just iterate over whole list and find the stones corresponding to this color. Um, yeah, so I find the stone corresponding to this color and remove it from the set, and in the end just output everything which wasn't removed from the set. Okay, let me open it here actually. Okay, my submissions, problems, my submissions. Let's open it. So that's the whole code. Pretty simple actually. Yes. So instead of having multiple ifs, I just put all the stones in this vector of pairs. It would probably be better to have map from string to string, but again, it's the first problem. It doesn't matter how you implement it. You just need to implement it correctly. Yes. So time complexity is not an issue here. Yeah. Put all the stones here. Then iterator all stones in the input. Find the stones corresponding color. Remove it and output the result. Yeah. So nothing really interesting happening in problem A. Hope everybody solved it correctly. Actually, I wanted to check if you solved it correctly. Yes. So let's check if you had any problems with problem A. Some of you managed to do it incorrectly. Let's see. No, not here, not here, not here, not here. Okay, that's just one. You forgot to output. Okay. It's obviously incorrect. Okay. What? If How did you get this? If false. How? You forgot to read this. Okay. Makes sense. If you didn't read the data, you can't produce the answer. Yeah, and you didn't test it because you're too fast to submit. So wrong answer test one, may it's possible, but if you pass test one, it's kind of hard to make it incorrect. Okay, second problem, you need to factorize a given number n into exactly k factors. So you need to produce a k integer, so product of this integer equal to n. Yes, integer should be greater than 1. If you don't have this constraint, you can output 1, 1, 1, 1, n. Yes, it would be kind of boring. Since integer should be greater than 1, what you need to do? You think about, again, so I need to factorize my number. Yeah. So if I factorize it in maximal number of multiples possible, so you just have factorized in prime factors. Yeah. So you can produce prime factorization of the number, and then if you need less than this number of factors, you can combine some of the factors, just group them, and remove those. Okay, so my solution is kind of boring, but okay. So let's say here. So if you have number, I don't know, let's get 60. Yeah. So it can be split in like 2 multiplied by 2 multiplied by 3 multiplied by 5. Yeah. Yeah. So if your k is greater than 4, it's impossible. If k is less than 4, you can just combine some numbers. So for example, if k equals 3, you can combine these two and you have 2 by 2 by 15. Yeah. Yeah. So you can get any number less than total number of your prime factors. Yeah. So that's basically the whole solution. So let's do it really quick again. So it's boring because it's very standard thing. I just build prime factorization of the number. If you don't know how to build prime factorization, learn how to do it. It's very simple algorithm. So that's it. Yeah. So I build prime factorization in square root of n time. Here it's possible to do it in n time. N is small, so it doesn't matter how. But that's kind of standard way how I usually do it. So it's you iterate all numbers up to square root of n, and just greedily take all the primes. If something left, then this leftover must be a prime. Yeah. So if something left, then I push it in my array in the end. That's it. So that's standard prime factorization algorithm. And now I check. So if I have less factors than k, then I output -1. If I have more, I combine them until I have it. And I combine it like this. So I just take two last elements and multiply them. You see, like this. Like this. There are many ways to do it. I just do it like this. So I just every time I combine last two elements until I have exactly k numbers. Yeah. Pretty simple, but very nice problem actually. So let's see again. So if you have made any mistakes, oh, Alex made not mistake here. Wrong answer test 11. That's fun. Let's find mistake here. Okay. So what you're doing here? So you build array, you put okay, so that looks like prime factorization for me. Yes. So if poly is not n, that's strange. What? PL is not n. PL. Okay, you rename them. Why you rename variables? I know. So this is x is actually n, and this n is actually k. Why you doing it like this? Okay. So while it's not k, yeah. Okay, k is actually okay. Okay, why it is divisible? I okay. I put x. Okay, you do it until you have exactly n. It will much more sense if you have less than n. Okay. If you have less than n, okay, and if you have exactly n, then you multiply the rest of the so first element multiply by the rest of this one. No, again, you forgot this last element. Yes. So here you need to divide by all elements up to square root of n. Yep. And here in the end you have some rest in this in this number y. You have some remainder. Yeah. This remainder is another prime. You forgot it here. Yeah. And that's why. Okay. And I believe you fixed. Oh, I believe you fixed it in the next submission. Yes, here it is. Yeah. So if something left in your number, you just push it as another prime. It's something you shouldn't forget when you build prime factorization. Yeah. So that's normal prime factorization. Okay. It makes sense. So it doesn't. The wrong answer test 11 actually. Not that easy to find. Okay. So again, that's it. That's problem B. Have any questions? No? okay, it's kind of simple problem. So then called force is slow, so I'm waiting for course force. Okay. Oh, here I waited some time until code force is finally solved. That's the only problem. Problem C. Problem C is another. I would kind of some kind of standard problem. We solved, I believe, some time ago, very similar problem. Yeah. So we need to build one string from another string by replacing some letters. Yeah. Yeah, but here you need to check if it is possible by replacing which kind of replace letters in pairs. So you want to swap some pairs, and yeah, so that's what you have. So you replace H with E and E with H. Like here you have H E E H. Yeah, and you need to check if it is possible to make one string from another string by replacing letters in some pairs. Yeah. So again, pretty standard. So okay. Yeah. So that's basically the idea. I will okay. It's just start. I will yes, I will. It's a little bit more complicated than this, but so basically what I'm doing here, I build this mapping. So which letter maps to which, and then in the end just check if this mapping works or not. There are many ways to do it. Actually, you can do it on a go. So you can remember which letter corresponds to which, and then if you see mapping which already existed before, then you do something strange. But that's actually much more easy to do it like this. So you build some mapping that should work, and then in the end just check if it works or not. Yeah. Here, okay, here I tried something strange. Oh, yeah. So that's updated version. So I do the mapping. So I initialize it with some simple mapping. So from C to C, very standard thing. Yeah. Then I get all the letters and build the mapping which should work. Yeah, and I know mapping in both ways because I know they should work in pairs. Yeah, so I make mappings in both directions, and then I check if this mapping work or not. Yeah, okay. Now in the end, we need to check that we have these pairs. Yeah, so for every element, the paired letter also maps back. So that's what we'll do. Yeah, so I'll just check. Let me stop. Okay, so here. So I check if I take letter C, look at the mapping for this letter C, the reverse mapping will be still back to C, you see? So basically I check that in my permutation, I only have cycles of size at most 2, if you think about it. So basically my mapping should be permutation. So every letter is bijection, yeah? So every letter maps to something and back, yeah? And I need to check that this bijection forms only cycles of size 2. Yeah, so if I move, so again, my letter H move to C and E move back to H. Yeah. So that's what I'm checking here. I check that my mapping is actually bijection. Yep. Not bijection, just bijection to itself. Yeah. Okay, so if I apply it twice, I have this. You got it. Okay, here I forgot to get okay ints instead of chars. Okay, there's some silly mistakes. But again, that's pretty simple problem, I would say, but it's technical problem. Yeah, so you need to carefully implement what so you need to build these mappings, check the mapping is correct, and so on. It's not easy problem, but like it doesn't have any special idea, but technical details are kind of untrivial. So you need some again experience in programming just to implement it without any problems. So let's find your mistakes again. Okay, like another problem is very easy to overcomplicate things. So here's clearly overcomplicated solution. You see, and in problems like this, when you have only technical difficulties, the trick is to make your solution as simple as possible. So it's easy to write, it's easy to validate. Yeah. If you overcomplicate your solution, it's very easy to make a mistake. Yeah? So okay, let's find mistake here. Try at least. Map from char to char. Okay, you can make loops over characters like I did here. Okay, like here, like these loops. Yeah, looks much easier than yours. Okay, but again, we make this mapping. Okay. Okay, that's overcomplication. You see, so we see if this mapping non-existent and if so if mapping exists, so exclamation mark means it not mapped. So if this letter is mapped and it is mapped to something which is not bk, or mapping to bk is not equal to ak. So if I already make some mapping and this mapping is incorrect, I make z equals 0. Okay, if z equals 0, you can just make this just exactly here and make return 0. That's what I usually do. So if I see some incorrections, immediately print impossible, return 0, and stop. So you don't think about it anymore. Okay. Else, make mapping in both directions. Okay, so this part is basically like my solution, but you wanna make checks, and so you build this mapping and check this mapping in the same loop. Should be fine. I would say you need to check this mapping in both directions, actually. I'm not sure if it matters. So you check if mapping for A exists, and here we check mapping for B. So probably need to do this if A exists and this if B exists. Okay, I'm not sure if that's what if that's a mistake. And here you pick Jeff if it's not then, and it can't if. Okay, why? You because you have two pairs. You have from A to B and from B to A. Yeah, you want to output only one of these pairs. I do it like here. You see, I do it like this. So I only output pairs from small number to large number, from small character to large character. Yeah? So that's how I avoid this problem that I have two pairs, A to B and B to A. Yeah. Okay, you do it like this. So every time you outpair, you mark all these numbers so you don't outpair them again. Okay. Okay, is it the only mistake? Let me copy. Submit. So I believe this part should be. Let's make so if A exists and it is not to be Duke, then z equals 0. If B exists, wait, if B exists and it is not to A, also no solution. And if not, then we do this mapping. That's something I like better, actually. So let's try. Probably not. Do we have a round? No. Not now. Okay. Yes, okay, it works. No, okay. Again, you overcomplicate solution, then that's why you made mistakes. Try to be simple. So when problem allows you, sometimes you have problem which kind of force you to write complicated solution. If you can write simple solution, write simple solution. Okay, that's something you get after some trainings actually. So that just try to do it. Just don't forget to do it. Don't just write the first solution you get. Yes, try to think at least a minute just to figure out what is the easiest way to do it, and just do it like this, okay? But not again. It's very it's very hard to balance. Sometimes you oversimplify things, sometimes you overcomplicate. It's okay. It will get you will get it with some experience. So let's find some mistakes of someone who didn't solve it. Wrong answer text 69. That's actually surprising. What can you do which only fails in test 69? Let's check 69. What is this actually? BDCC. Okay, so you didn't make. Okay, so you need, yes, you need to remember mapping in both direction. Well, at least you have very short code. Okay, you have minus this minimum and maximum. Oh, that's interesting. Okay, it doesn't matter. Okay, it doesn't matter. Okay, if you have pair of characters, it doesn't matter which one is which. Okay. If at least then you have okay. Okay, so you remember mapping only from small character to large character, and if you find the large character and it's, but you don't you make this, okay, answer, okay, you make two different mappings, okay, from small to large and from large to small. Why? Okay. Hmm. No, okay, yes, there exists. Nice. Test 69. Yes, here you have this problem. So in this pair BC, you have C as the largest character, and in this pair CD, C is the smallest character. Yeah. So you kind of, so okay, so you use C twice, once in this mapping in ends, in this mapping, and you did notice that you have the same character here and here used for different mappings. Nice mistake, actually. Okay, but you try to make simple code at least. So you try to make simple code, but unfortunately, it's still incorrect. Also happens. Okay, let's go to the next problem. Next problem is about. Oh, this is actually a fun problem. This problem I got in my Blitz contest. So we had Blitz contest a few days ago, and I failed miserably. I was kicked out in the first round. I lost. But that's one of the problems I got in the first round. So I thought it's kind of cool problem, so I will give it to you to solve. So you have two arrays, and you need to pick exactly k numbers from 1 to k, once each number. So you need to pick all numbers from 1 to k, each number only once, and you need to pick half of them from first array, half of them from second array. You just need to check if it's possible or not. No, okay. The idea to pick for each number we need to so we only care about numbers from 1 to k. Yes, for each number from 1 to k. Okay, let's see. So if you look at numbers from 1 to k, they can split into two groups. So it's array A, that's array B. Yeah. So if you take any number from x from 1 to k, yeah, there are just few options. So this number may exist only in the first array, it may exist only in the second array, or it may exist in both arrays. Or sometimes it doesn't exist, then you just output -1, yes? Yeah, so some numbers exist only in array A, some numbers exist only in array B, and some numbers exist in both. Yeah. So how do you solve this problem? You think, okay, how would I construct something like this? Yeah. So I need to pick some k over 2 numbers from here and some k over 2 numbers from here. Not a segment, just okay. Okay. So you pick. Okay, no, it's not a segment. So I will. So you pick k over 2 numbers from here, k over 2 numbers from here. So I think, okay, how would I do it? No. So these numbers which are only in A, you should take them from array A, because there's no way to take them. Yeah. If you have here, you have more than k over 2 numbers, then you already cannot build what you need. Yeah. Uh, no solution. Yeah. Same thing here. Numbers which exist only in array B, if you have more than k over 2 numbers, then solution is no, for the same reason. Yeah. If both these are not true, so if you have less than k over 2 numbers here, less than k over 2 numbers here, then again, so you build some, let's say a prime, b prime. Yeah. So you put something here and you put something here. Yeah. And all the rest here, you can fill from this middle group. Yeah. Because you can put these elements anywhere. So you just put them here and here. And now you have k over 2 elements here and k over 2 elements here. Yeah. So that's all. That's what you need to check. You need to check that numbers which exist only in A are no more than k over 2, and there are no more than k over 2 numbers exist only in array B. That's pretty cool idea, actually. After you realize what you need to do, the code is actually pretty simple. So let me implement really quick. So what I do here, I do it in a cool way, actually. I calculate state for each number. I calculated state. So if I have this number in array A, I OR this state with 1, you see, and basically I use 2 bits for each element of array st will have 2 bits. First bit means I have this number in array A. Second bit means I have this number in array B. Yeah. So the value of this number will be 0, 1, 2, or 3. Yeah. So I have 4 different possible values, yeah, depending on combination, yes, of this. And so let's put it here. So elements here have st equals to 1. Elements here have st equals 2. Elements here have st equals 3. Yeah. And I also have st equals 0 for elements which just not exist. Yeah. And just need to check. Okay, so here I made mistake. Okay, let's skip it to avoid some embarrassment. Back. Yeah. So what I'm doing here, I calculate how many elements have each state. So for each state, I calculate how many elements have this state. Yeah. And here I in the end I just check to show me. So I just check. If I have elements only in A more than k over 2, if I have elements only in B more than k over 2, if I have at least one element which do not exist, then answer is no. If none of this is true, then answer is yes. Yeah. Cool problem, because again, you need to think, you need to understand what's going on, and then you have just implement. Okay, actually, not that much code, you see. So again, here it's a lot, not. But let's see what you can go wrong. Okay, wrong answer is 1. Why you don't test it locally? I don't understand. Wrong answer test 1 means you are very lazy to test it locally. Okay, I will not try your mistake. So if you have wrong answer test 1, I will not find your mistakes. That's my protest. Good. Any questions? No. Okay. Just check if I hear you. Okay. Problem E. Problem is nice problem. So you given some powers of 2. I didn't draw anything because so let me draw something here. Chim. So you're given some powers of 2, and you can combine them to make another powers of 2, and you need to combine them in minimal number of blocks. Like here you have, like, let's test it. Let's try example 1. So you have some 2 power 1 plus 2 power 1 plus 2 power 2 plus 2 power 3 plus 2 power 3. Yeah. Okay. Not plus. You have so So you have these items, yeah? So you need to combine them into groups such that in each group, the sum equals power of 2. For example, here you can combine them through first 3 and the first. Okay. Okay, let's combine these 3. Let me actually let me write them in binary actually. So please. So you have 2 power 1. It's as 1 0 1 0 1 0 0. Yeah. Oop equals 1 0 0 0. Yeah. And you combine these two. 1 0 0 0 plus 1 1 0 0 0 equals 1 0 0 0. Okay, and you need to build minimal number of these sets. So how I usually approach problems like this? I usually first think, okay, I need to minimize something. Let's build, let's find some, again, so you want to find some lower or upper bounds of your answer, yeah? So you want to think, okay, answers at least this, or answers at most this, yeah? And then think around this part, yeah? So you're looking for some number, yeah? For some answer, some optimal something, yeah? And you make some observations which tells, okay, my answer is at least this. So it is bounded to this, or is it at most this? Then you make some more strict bounds. Okay, make strict this, then strict this, and at most this. And at some point, when these two bounds meet, yeah, then you find your answer. Yeah, this kind of way of thinking how you find the desired result. Yeah. So, for example, here I want to minimize the result. Yeah. So let's make some bounds for this. For example, okay. 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 Hard to make minimal bounds. For example, you have the answer is at least 1. At least 1 lower bound. Yeah. Okay. Yeah. Okay, let's make some more interesting bounds. For example, so if your answer is so in every set, the sum equals some powers of 2. Yeah. So if you look at sum of all integers, sum of okay, 2. No, 2 a is just power. Yeah. Sum of all these numbers. Yeah. So in my case, it will be 1 1 0 0 0. You see. Because in each number I have some power of 2, I need to find minimal number of powers of 2 to split this number. So this number can be splitted in at least 2 powers of 2. Yeah. So if you look at number s, what is the minimal number of powers of 2 you need to compose to get number s? Yeah. This number is just number of these 1 bits in the representation, you see? So I need at least 2 groups. Yeah. Just because total sum equals this. Yeah. Yeah. So this is my number in binary. I need to split this number into some parts, and each part is a power of 2. Yeah. So I need at least 2 such parts because I have 2 ones in binary representation. Yeah. Again, it's good lower bound to get this. Now I think, is it always possible to achieve this lower bound or not? Yeah. And in this problem, it turns out it's always possible. No, why it's always possible? No, because let's look at the lowest power of 2. It's always possible to get a subset with this power with this sum. Okay, let's new diagram. So imagine the sum of all 2 power ai equals something. So it's something. Here we have 1 0 0 0. Yeah. No, because each element is a power of 2. Each element is a power of 2. Let's add them one by one until we get this result. Okay, so again, let's remove all powers which are greater than this. So these powers removed from this set. Let's leave only these powers. And then I will add them one by one to the set until I have something at least this. Yeah, so we add, so we have 2a1, a1, plus 2a2, plus and so on, until we have something which is at least this. Okay, and because you have only powers of 2 here, you cannot get you can get kind of jump up as well. Yeah, so the last power you add is just make this equal to this. So you cannot make smaller than this number and then greater than this number, but because you have only powers of 2. You can think about it like this. You can think about it like this. So total sum equals this. So here we have this one bit. Yeah. So you have some you have some subset here which gives you this one bit. Basically, yes. Yeah. So if you take this subset, you will have something, I don't know, something maybe greater. Yeah. So imagine you pick some elements until you have this one bit. Then you have something else. You have you have some sum of elements of some 2 power bi equals, I don't know, 1 0 1 1. Yeah. Then because you only have powers of 2, you can remove extra elements. Yeah. So you have this one because you have one of them bi equals 0. Yeah. If you remove it from the set, you have 0 here. And now again, here we have 1, but because you either have 2 zeros or you have 1, you can remove this or you can remove this, and you can remove this one. In the end, you have this subset which exactly equals to this. Okay. Okay, not very formal proof actually. So, is there a way to prove it easily? Actually, let's check if problem authors have easier proof than mine, because my proof is mostly like let's check. Maybe there is easy way to prove it. Okay, proof is easy. You can prove it as a practice. Okay, let's leave it as an exercise also. Okay, okay, that's something I also do all the time. Okay. Thank you, dear. Who? Let's see, who is Prince of Persia? Okay. Help. Thank you very much. So that's it. So that's the full solution. So we need to calculate the total sum, count number of ones in the bit representation. Yeah. Now it's a little bit tricky part. So you need to carefully write down this number. So I need to calculate. No. So you need to calculate this number in binary. Yeah. So you can just do it actually. So you can just build this binary representation because powers are kind of small. Yeah, so have powers up to million. So you can make array of million digits and just operate with like million digit binary number. That's basically it. So I do it like this. Let me show. So I make it a little bit more than million because I have million multiplied by n. So it's 1,020,000, but I do a little bit more just to be sure. Yeah. So here I calculate number of times I see every power of 2 here. Yeah. And here I kind of promote them to the left. Yeah. So I take each power of 2 and half of it promote to the next digit. So basically it's like when you calculate sum of many numbers, yeah, and you kind of allow two digits be more than one. Okay, let me show you. It's hard to imagine. Like for this example, so I have I have 1 plus 1 plus 10 plus 100 plus 100. Let's add some more. Let's add some more. Okay, let's plus and plus another 10 and plus another like this and plus another and plus another something. Yeah. So imagine you calculate sum of all these numbers. Yeah. So what you can do, you calculate sum for every digit. Then you have 2, 2, 3, 2. Yeah. In binary. Yeah. Now you just need to make a proper binary number. And you do it by just transferring these bits right to left. Yeah. So you take this 2. 2 is actually so 2 is actually 0. Yeah. And you transform this 1 to the left. 1 to the left. So now here you have 3. See? So 3 is 1 and another one moved here. Yeah. So now you have 4. 4 is 0 and 2 transport here. So now we have 4 here. So again, it's 0 and 1, 2, 2 goes here. Yeah, see? And again, you have 2, again, you get 1. Yeah. So I kind of go right to left and just make it a proper binary number. You can do the same with decimal numbers, by the way. So for decimal numbers, if you calculate sum of long decimal numbers, you can calculate sum for every digit and then just normalize it in the end. So that's what I'm doing here. I calculate sum for every digit. So I make binary number with digits more than 1, if it makes sense. Okay. And then just normalize it in the end. So I make all digits zeros or 1. Okay, I don't make digits actually. So I just add them to the result. So this AY modulo 2 is just my digit. I add it to the result. That's it. That's the whole code actually. Okay, let me show you the code. My code. Where is my code? Number. This one. Very short. So that's the full solution. Very simple. Yeah. But it is again, it's a mathematically interesting problem. So you need to understand what's going on and find the mathematical solution. After that, code is very simple. +6. How did you make +6? Time limit. Oh, how do you get time limit? That's interesting. Let's see. Okay, you do something strange. Okay, so this part is the same, but you don't make a race. You make a map. Okay, so for every digit, you remember this sum, make it in the map. It would be necessary if you have large numbers here, but you have up to 10 power 6, so up to million. So instead of maps, you can just have an array of size million. Will make things much easier. Let's see. Okay, steps. Okay, so you find the lowest power of 2. Okay, find the frequency. Not just no sum for this digit. So you find the smallest digit, find this digit. Yeah, erase it. Okay, if it is odd, increase steps. If it is more than 1, plus equal. That's fun. So this give you time limit. Okay. So it's basically the same solution, but you make it not over arrays, but over the map. Yeah. Okay, so time limit is strict here, right? So 1 second for million operations. Okay, okay. So they doesn't want you to do it with maps. Fun. No, okay. You need to you need to optimize a little bit here. Okay, but you managed to do it, right? So no problem. Yes, eventually you solved it. Yes, just by doing this. So just by moving from maps to arrays. Makes sense. Makes sense. I did the same in the last problem actually. In the last problem, I tried to do it with maps. We will go to it. Yes, and it turns out you need to have arrays instead of maps. Okay, also have time limits. Also with maps. No. You don't have fast IO. That's why. Because of the slowest input. Yes, because of this. Okay. Okay, you use normal templates again. That you can use templates here. Just remember, just save your template somewhere and just reuse it. Why you have this? So what's going on here? Why you have all this crap? What doesn't make sense to have a lot of crap and don't have fast IO kit? You just making life harder for yourself actually here. Okay, so this was problem E. Problem F. Problem F is actually a very standard problem of for graphs. We need to do like show you. So what we have in problem F? We have a graph. Yes, we have a graph. We need to find the path from vertex 1 to vertex n. Yeah, such that total length of all edges is at most t, and number of edges, yeah, the guess is maximal possible. What we'll do, we will reverse this condition. So instead of finding for this given t maximal number of edges, I will find for every number of edges minimal time. Yeah, so I will do this like this. dvk will be minimal sum of edges for path of k edges. Yeah, so I will put this length of the path into my dynamic programming. And okay, if you look at from this perspective again, so not from given t find number of edges, but given number of edges find t. Yeah, you will see that you actually have a standard shortest path problem. So it's basically what Bellman-Ford algorithm does. Yeah, so Bellman-Ford algorithm calculates for every number of steps. Yeah, calculate the shortest path. Very standard. Yeah, so that's what we'll do here. We will make basically standard Bellman-Ford algorithm, like in one of the most standard way possible. So I just like this. So I will calculate this dynamic programming. Okay, I switch parameters here. So in my program it's like this. Yeah. So because I calculated layer by layer usually. Yeah. So I increase k. Yeah. The only trick here, I don't know if anybody had the same problem. Problem F. Yeah, you probably have the same problem. Yep. The only problem you may have is memory limit. That's what something I was thinking about, because 5,000 by 5,000 is already like 25 millions. Yeah. So I need this array. I need array of size 25 millions, and I have only 200. So I have like 10 bytes per element. That's enough. Yeah. But I didn't want to make two arrays. I probably have enough memory to have two arrays. Normally, because you need to restore the path, I would make two arrays. Yes, you make D and you make P KV, yeah. So D calculates the shortest path, and P calculates the reverse pointer to restore the answer in the end. Yeah. Yes, and I probably could did like this. Okay, 200, it's enough. So my program works in. Let me check. Yes, I use just 100 megabytes. Okay, I could use twice more memory easily. Yes, for the second array, but I decided I would save some memory here. So my program used only half of its memory. I use only array D just to save the memory. So my program is even overcomplicated actually. So I use only array D, and when I need to restore answer, I basically do the same thing second time, just with this restoring the answer. Okay, I'll just show you how it's done. So if you see some problems like this, when you need to be careful about your memory consumption. So okay, just reading the graph, this boring part. So here, so that's my array. Okay, I will use only this array for the whole program. Okay, no plus the graph. So this is my graph. No, graph is small. It's 5. Okay. Here. Okay, so that's basically dynamic programming. So this here I have mistake, doesn't matter, I will fix it later. So that's basically main dynamic programming. Yeah. So I is my step, U is my current node. I take my current node, look at all possible edges, and find the minimum over all possible moves. Yeah, very standard for Bellman. Okay, maybe sometimes you done in reverse the same thing, but it kind of that's it. Sometimes you reverse the graph, so you look backwards. Here I look forward for simplicity. Okay. So you need to build path from right to left, but okay, who cares? Okay, here's something strange. Yeah, and in the end, because I don't have this array of back pointers to build the path, yeah, I just repeat the same process. So instead of having the pointer, I just calculate which move I actually made to make this result. Yeah. So I look at all possible moves once again, like here. The problem here that if you implement like this, you need to duplicate the code. Yeah. So here I calculate the result, and here I check which element give me this minimum. Yeah. So I find element which give me this minimum, and just move to this. Yeah. Move to make this transition in my name program. Yeah. Okay, hope it's clear. Then I fix some mistakes, a lot of mistakes. Okay, I debug. Here I had mistake again because I had in different order of these elements. Okay, it was silly. Yes, and in the end I calculate not the shortest path, but not the longest path, but shortest path. Also fixed. But that's it. That's because let me show you the full code. It's not actually long. So that's basically the full code. Yes. So again, I have one array, two-dimensional array. Array of dynamic programming. Yeah. This array tells me parameter. So first number is number of edges. Second number is my current node. Yeah. I fill it with elements t+1. t+1 is basically infinity. Yeah. So if number is greater than t, it's basically infinity. Yeah. So I fill with infinities, fill starting value of 0, and starting value is n-1 because I go right to left in reverse order. Okay, doesn't matter. Yeah. Here I take the element, make all possible moves. See? So and update my result with again shortest path of I-1 edges from node V plus this one edge. Calculate minimum. And then in the end, I restore the path. So I take this current state of my dynamic programming and make one more move. Yeah. And I make the move which gives me this minimum. Yeah. So I find the element which gives me this minimum, make this move, break. Continue. Okay. So that's how I implement the problem when I think I need to save the memory. In this problem, I actually don't. So now I understand that I have twice more memory than I actually need. Okay, I could just here, I could just here, okay, let me show you. So how I would normally do it, normally I would do it like this. So I would say, so so if d is less than diu, I will make diu equal dd, and I make p of iu equals to v, yeah, like this. So I make another array p, which stores the pointers. See? And I will just use these pointers to restore my path. Yeah. So here I don't need to make this second loop. Yeah. I just make this like u equals this p of u, like this, yeah? Instead of the second loop. Yeah. So that's how I normally implement it. So you create dynamic programming and reverse pointers. And here you just use reverse pointers to restore the path. Yeah. But you don't need them actually. If you really care about using as less memory as possible, you can just save memory here. Only use dynamic programming array, then don't use reverse pointers. Okay, just something to think about if you get yourself in some tricky situation when you actually need to think about saving as much memory as possible. But again, that's it. That's problem F. Any questions? No? Okay, we have two problems left. Problem G is fun problem. Okay. So what we do in problem G, we need to make all the numbers have the same common divisor, yeah, greater than 1. And we do it by performing some strange operation. Okay. By performing some strange operation. Yeah. So we replace two numbers with these two numbers. Yeah. So what I usually do, I start thinking with some small examples. Yeah. So starting some small examples. Okay, just move. I just read statement, do something, think a lot, read. Okay, I read examples and so on. Yeah. So let's start with two numbers. If you have two numbers, yes, and they don't have any common divisor, yeah, then let's make one operation. You have x minus 1, x plus 1. Yeah. Then I think, okay, these two numbers, do they have any common divisor? So I see how the situation improves. So if I apply this operation, how can it be then after this operation, I have some common divisor? So I didn't have it before, but now I have some common divisor. Yeah. So I'm looking about common divisor of these two things. Yes, and how you can make a common divisor? Basically, you apply Euclidean algorithm. Yeah. So if you apply one step of Euclidean algorithm, you have 2y here. So basically, you move from y to 2y. Yeah. So now you see, okay, after applying this operation, I only introduce one new factor, that is 2. See? So it only may happen if my numbers are divisible by 2 now. Yeah. So I cannot introduce any new interesting divisor except 2. So if my numbers weren't divisible by the same number before, and now they are divisible by the same number, it only may happen if they are not divisible by 2. Okay. And after you do all this, so again you think how this operation helps you to create a common divisor, and you see that the only common divisor that you may create is actually 2. And now you have much more simple problem. So you care only if number is divisible by 2 or not. And you think, okay, if I have two odd numbers, after I apply this operation, I have two even numbers. Oh, nice, yes. So in one operation, I can make two even numbers. Yeah. And then you see, you just recall other cases. So what will happen? So for example, if I have two ones, I make two zeros. Two odd numbers transform to two even numbers. If I have three odd numbers, what can I do? and you just write down, okay. You transform these to two numbers, and then you have 0, 1, you transform to 1, 1, and to 0, 0. Yeah. So any sequence of three ones can be transformed into three zeros in like 1, 2, 3 operations. You see? And again, you just play with these zeros and ones and see how many operations do you need until you have all zeros. Yeah. And you, again, it's kind of easy to see from this point. So after you limit yourself to only divisor 2, yeah. So you only care about divisibility by 2. Yeah. Now you have only odd and even numbers. You have zeros and ones, and we love zeros and ones. Yes, it's much easier to think about it. Now you have only zeros and ones, and then you can play with these sequences of zeros and ones and see how they transform to each other. And you want to make all zeros, so you kind of want to eliminate all ones. So you see, how can I eliminate all ones? Okay, if I have two ones, I can eliminate in one operation. If I have some odd size sequence of ones, I need something else here. Yeah. So to remove this last one, I need another two operations here. And that's basically it. So that's the full solution. So what I'm doing here, I just play with it like this. I check if I have any corner cases, because if this extra one is the leftmost, is the rightmost, it turns out it doesn't matter. So if you have 1, 0 or 0, 1, you still can transform into 0, 0 in two operations. So it doesn't matter. No corner cases. Very simple problem. So here I check that I have some greatest common divisor. Okay, cool thing actually, you can initialize greatest common divisor of 0. 0 is basically a neutral element for GCD. Yeah, so that's how you find greatest common divisor of multiple elements. So I check if it exists, just output yes 0. If it doesn't exist, then I make them all even. So again, I transform it to a sequence of zeros and ones. And here, okay, okay, here I find sequences of ones. So again, so C is length of my current sequence. If I see one, I increase size of sequence. If not, okay, this line should be swapped because I'm stupid. Okay, you can swap these two lines. Okay, so but you add to answer half of this length, but if the line is had odd length, then you add two more operations to remove this last one. And that's it. And now I found, okay, now I spend a lot of time to find this stupid mistake. I found a lot of time. Let me look for it. Okay, I spent too much time finding this mistake, but I didn't submit. Okay, so I did it before. So I did it in local testing. You see, so I'm good for me. Okay, let's see. I'll just watch myself finding stupid mistake. Okay, finally I found it. Okay, so I make C equals 0 and then add it to result. It doesn't make any sense. Yes, you need to first add it to result and then make it 0. Okay, so that's problem G. Kind of interesting problem. Yeah. So I like this idea that you need to make some common divisor, but after you research what your operation does, you find out you can only make a divisor 2, and then it's completely different problem. Yes, instead of making common divisor, you just need to make all elements even. Yeah, so you kind of simplify this simplified problem, just another problem. It's not about GCD anymore. Yeah, it's about parities. Yeah, so it transform problem from this type to this type. Just cool thing. Okay. Okay. Hope you liked it. Who solved it? Wrong answer is 4. Okay. How can you go into wrong answer test 4? I'm just curious. Test 4. 86. Okay. That's too much. Oh, okay, you do something really complicated. Something really complicated. So what is your last solution? Is it correct? Okay, yes, and here, okay, you're fine. So you try to do something strange. So you try to introduce some strange common divisor and doesn't work. Okay, last problem. in the last problem is pretty standard problem of two pointers method. I have the full. Okay, let me show you again. Let me. We fixed the. So not me, but Mike Mirzayanov finally fixed the edu section, so you can again. Let's check it's actually fixed. You can again enjoy the 2 points method. Yeah, the educational section called forces. So I have a full lesson about 2 pointers method. Just advertise myself. And okay, so okay, so here I believe. So if you watch this lecture, you can get the point. So let me can read there. So okay, I use code in Python because I can. Okay, so how I usually do 2 pointers methods. Here I do it like this. I move one pointer. So I usually move one pointer with for loop and another pointer with while loop. Okay, so I make r++ here, but l++ here. Yeah, and it's kind of easier to track. Yeah, so you always move one pointer, and second just kind of finds the optimal position. Okay, just I will just leave it to you. Just later you can watch this lecture and good lecture actually. I actually recommend to watch if you want to learn 2 pointers method. What I will do here, again, I will use 2 pointers method. I will have one pointer, another pointer, and my segment is good if I have at least k equal elements. So how to check if you k equals element? Now you calculate how many elements you have for each element. So you have, again, map of counters. Yeah. And then you just need to find the maximal counter. So you have another, so what I tried to do, let me actually, so what I try to do here, I make this map for counters, and I make this set to find the maximal counter. Okay. Then I had time limit exceeded, and I need to rewrite it with erase. But okay, the idea of solution is kind of the same. Okay, so here I do it like this. I move the left pointer with my for loop and right pointer with my while loop. Yeah. So basically what I'm doing here. So I have this array. So I fix the left pointer here, and then I move the right pointer. Right pointer is here until this segment is good. Yeah, until I have at least k elements here, equal elements. And then I move left element one position here and again. So I have this segment, and until while segment is bad, I move right pointer. So this while segment is bad. Yeah. So it means so my maximum is less than k. You see. So while my maximum is less than k, I move the right pointer here. You need to increase r somewhere here. Yes, you need r++ here. Okay, right, r++. Yes. Okay, so r++ here. So you move right pointer until you have good segment. Here you check if you have good segment, you add this rest to the result. Okay, so number of good segments will be so your right border may be here or here or here or here. So for this left border, right border may be here, here, here. So you have this number of good segments. Okay, have some stupid mistakes. Yes, 0. Let me watch. I will watch myself finding stupid mistakes again. Because you can't do rand. So rand doesn't work like I supposed to do. So I need to find maximal element in the set. It doesn't work like this. Yeah. What is the easiest way to find maximal element in the set, actually? Is it the easiest way? I don't know. Okay, so that's the full solution. Let me show it here. So it's long. So let me show you it here. Time limit test 115. So you know, yeah. So sometimes you get outcomes like this, and that's not fun actually. So that's the full solution. Very short actually. So again, let's read it line by line. So what's going on here? We have one loop which moves left pointer. I didn't upload last video. Okay, I will upload it. I probably didn't publish it. I uploaded, I didn't publish it. I will do. So I moved left pointer with this for loop. And then move the right pointer with this while. So I move right pointer while I have bad segment. So this is just check that I have bad segment. Yeah. So if I have bad segment, I move right pointer, update my result. If I have good segment, I add number of good segments to the result. Okay. You could probably move this R to N plus. Yes, you can probably move this R to N plus 1 and then avoid this if. Okay, up to you. Finally, here, I move the left pointer. Again, when you move left pointer, you need to remove one element from your segment. Yeah. So I remove this one element, update the counter, update the maximum set, and that's it. Okay. Very nice short solution. Unfortunately, it gets time limit test 115. So I needed to. Okay, how much time? Okay, 5 minutes to replace it. Okay, so this solution does exactly the same, but with arrays. Yeah. So instead of set, I can have arrays. So what we need to change? First, we need to transform my array to array of small numbers because I have array of counters. So I had map of counters. Now I have array of counters. Yeah. So we do it like this. So I just so that's my normal way how I compress coordinates. Okay. So I get all the numbers and replace them with the index in this sorted array. Yeah. So basically, this operation transforms numbers to small numbers, but preserves the order. It's like integer compression, sorry, some coordinate compression, something like this. Yeah. So now instead of map, I can make vector here. It would probably be enough, but I want to remove the second set as well. So instead of second set, I have this vector again. So for each number of elements, I remember how many times I have this number of elements. So this second array is counter of counters. Yeah. So you see this. I do something like this. Yeah. So my maximum is maximal index. So the second counter is non-negative. You see. So here updates looks like this. Again, I remove this from the second counter, update first counter, add it back to the second counter. You see? So it's basic. Okay, let me show them both codes at the same time. No, my submissions. Wait, sorry. So it's the same thing. Let's hear, yeah. So you need to remove it from the second, update, and add it back. So this I do kind of the same, but instead of sets, I have array of counters. So I remove it from the second set, update, add it back, and then update my maximum. Maximum can be changed by only one because of how the problem works. So I don't care about this. Yeah. And here I remove element. Again, I remove it from the second counter, update, put it back to the second counter, update maximum. Okay. And it okay. So after that, it's much faster. So it's half a second. It's like at least 6 times faster than the previous one. So, okay, 115. Let me look, test 115. Yeah, it's even faster, you can see. Yeah, so I kind of know it speed up the solution, but I hoped that problem authors are not that not that bad. So they just allowed me to use sets here. But sometimes problem authors want you to optimize your solution. Because it's actually a good skill to optimize your solution a little bit. Again, okay, actually it is kind of asymptotical optimization. Yes, so we remove this log factor. Yes, so we had no, again, we still have log factor because we sort in the beginning. So I have n log n in the beginning. Yeah, so this part is n log n, but everything the rest is linear now. Before I had total, so I have log n everywhere here, so it was still n log n. Yeah, but this log was from these binary search trees inside sets. So it is slow. So sets are much slower than vectors. It kind of makes sense, but okay, let's read the solution. I don't believe you solved in 2 minutes. Sorry. You're probably smart, but not. I don't buy it. Okay, this looks more promising segment. Okay, this more segment tree. Why you need segment tree? That's interesting. Why you need segment tree? Okay, so you have two pointers method, but to check if segment is good or bad, you do segment tree. Okay. No, but yes, you see, you update one element and check. So basically, instead of my sets, you use segment trees, and it is fast enough. Yes, it's actually surprisingly fast. How do you say segment trees? Normal segment trees. Interesting. No. Segment trees are faster than sets. That's true, but I didn't expect it to be that fast. Okay, good for you. Good for you. So if you solve it using segment trees, means you know segment trees at least. Okay, so that's it. Thank you for watching. See you next week.